Welcome to rigorous training in longitudinal data science, Radiance.
Hello and welcome to this course discussing version control and sharing with GitHub. So let's start discussing a little bit about reproducible workflows and why they are important. I think the principle that is presented here on the slide is quite important. So as we start doing computational social science, so we use more data and code in order to do complex analysis and present complex graphics and results. The paper that actually is published and is peer-reviewed contains a smaller and smaller proportion of our entire work. It's just the tip of the iceberg for the work we have done. So now it is not enough to just share our paper with the results, but it's increasingly important to actually share all the code and the data that actually created the results that are presented. And workflows here refers to any practice that you use in order to create those results. So this is a combination of the data you use, the code you use, the way you organize your work, and your documentation for this entire process that leads to some published results that you share with others. So let's cover a few basic things before we go and discuss version control and how you can use that to document your work. In general, it is recommended to have everything that is related to one particular project or a paper in a folder. Often computer software will call this the working directory. And it's really important to have everything in one place because then it's much easier to share it with other people. Another reason why this is important is that we can use relative paths. So once we define what is our working directory, the place where we have everything related to our project, instead of using absolute paths, so saying the entire computer path to that to a particular file, for example, we can use relative paths. So saying relative to the working directory, to our root, where is a particular file. And the advantage of using these relative paths is that if we share our working directory with someone or we use it on a different computer, all our code will work once we set up the working directory. So it doesn't matter if we would use a different computer or a different operating system. In general, it is also recommended to spend a little time to think how to organize your folder structure so it's easier to find what you're looking for and it's easier for others to understand how you stored your files. And generally, it is good practice to have scripts or code for everything you have done. So try to avoid changing things, for example, in Excel or doing other things that cannot be traced. Because if other people try to reproduce your work, they won't be able to do that unless it's written down somewhere and it's explicit about exactly what you have done. So in general, it's good practice to have scripts for everything you're doing, from creating the folders, copying files, to data cleaning, analysis, and presenting of the results. Another good practice is never to modify raw data. So let's imagine you use secondary data, you download data created by someone else. It's always good practice to have it somewhere and never modify it. So you can import it in your statistical software and then you can work with it. But if you want to save any changes, always remember to save in a new file. And if something goes wrong, you can always go to the original raw data. And also this ensures that other people can download the same raw data and they can reproduce your work. Another small thing, in general, it's good practice not to have spaces in the names of your files and folders. This is because some computer software or some operating systems do not work well with spaces. So in general, it's a good practice to avoid them. Another good practice is to regularly back up your work. So you can use GitHub like we'll discuss in a few slides. You can use Dropbox and other services and always make sure that you have a backup of your work. Another useful thing, depending on the kind of analysis you do, is to set up the random seed. So random seed is the number from which any kind of sampling or any random process starts on your computer. So for example, let's imagine you want to sample, to randomly select some cases from a data set. Every time you do this, you'll select other cases. But if you set the random seed, then everyone will be able to select the same individuals if they have the same random seed and the same process for selection. And this is very important when you do analysis that involves some kind of iterative process, some kind of like bootstrapping or other types of analysis where it's actually you have a random process working in the background. So this is another small thing that you can do to ensure that everyone will have the same results as you have by setting up a random seed at the beginning. This could be any number as long as it's written in your code that will ensure that other people can reproduce your work. If you use Rstudio, which is a very popular interface to the software R, which is used for computational social science and data science, you can set up something called Rprojects. And these are very useful because they're kind of an easy way to set up your working directory and a few other things that can help with your workflows. So if you create the Rproject, automatically in the background it sets up your working directory. So your working directory would be wherever you have the Rproject. Automatically then you can use relative paths to, for example, open files. It's much easier to share and open these files from other computers, and it's integrated with other tools like version control and packages like Renv, which help with reproducible workflows. So if you're using R and Rstudio, I recommend you look into Rprojects as a way to facilitate reproducible workflows. It's also good practice to have kind of a consistent way to organize your work. Here I just give you an example how you could organize it. You could do it in a different way as long as it's clear for other people how things are organized, and also if you try to be consistent in time, so it's easy for you to find the files. So here, for example, we have a folder called data, and within that we have a subfolder called raw, and that's where we'll have all the raw data, and a subfolder called clean, where we'll have all the clean data. Then we have another folder called output, and here we can just save all our outputs. And here we have two subfolders, one for figures and one for tables. We have a subfolder for documentation, one for our paper or report, and one for our scripts. And the code I show you here is actually code from R, so you can create all of these folders directly from R, and then they will exist on your computer. You can run this code just once, and then you have everything set up to start doing your work. And this is an example of the folder structure. So this is how it would look like once you set it up. Another important thing to note and to share with other people is the session info. So session info in R is a command that actually prints all of these results you see here on the slide. So it tells us the version of R, the platform that we're using, the language that we use, the packages, and so on. And this is really important because packages and statistical software change a lot. And in order to ensure that people can reproduce your work, you need to be very explicit about exactly what you have used. Everything from language to operating system to the version of the packages that you used. And the session info command is a very easy way in which you can get all of these and you can share it with other people. So if they try to reproduce it, they will be able to ensure that they use the same version of packages. There are a few packages in R specifically that are very useful for reproducible work. One of them is called Renv, and I mentioned this before because it's actually very well integrated with Rstudio packages. And what Renv does is actually it installs all the packages that you use locally in your working directory. And this is very useful because as time passes, you might be using different versions of R or different versions of packages in different projects. And you want to make sure that you get consistent results. So imagine you submit a paper for review, a year later you get the feedback and you need to redo the analysis. By then there are new versions of R, new versions of the packages you have used, and your code might not work anymore, so you cannot reproduce the results. Renv helps sort this problem by enabling you to use the exact version of packages that you used 1 year ago. And in that way, you can reproduce your work, your code will work like before, and then you can continue where you have left off and do the changes that you need to do. Other useful packages in R are package versions. So this is a way in which you can use the old version of a package. So imagine somebody says, oh, I have, version 0.9.5 of tidyverse, and that's what you need in order to create this graph. Then you can use this command in order to run that particular version of the package. Alternatively, you can use the checkpoint package. So this is a way in which you can actually go back in time and use the packages that were available at a particular point in time. Other useful things to keep in mind. One is it's good to have consistent practices in how you write your code. And different organizations actually have these practices written down. So for example, in this link, there's a guide for how to write our code that is used by the team at Google. So this will ensure that everyone in that particular team writes code in the same way. That makes it easier to read, easier to share, and to understand what people have done. Other things to keep in mind, it's good to have your scripts self-contained. So imagine just having a script, for example, that does the data cleaning, and it's very clear that it just needs the raw data, and then the output is the clean data. It doesn't depend on anything else. And also it's good to have tests in your code. So you can have some tests to make sure that, for example, the data has the same dimensions as expected, the results are the same as what you had before. So this just ensures that if changes have appeared, you would get the error and you can check and see exactly what is the cause. Another good practice is to comment very often on what you're doing. While things are very clear when you write the code, why exactly you're doing that particular thing, as time passes, or if you share the code with other people, it will become less and less clear why you have done something. So this is why it's really important to comment your work and to have good documentation for your code. Another good practice is to separate different stages, especially separate data cleaning from analysis. If the analysis is complicated, you can have multiple steps for the analysis. And for example, you could have a separate script for creating tables and graphs and so on. Also make sure that the variables you create or the columns you create in your data or the new data sets you create or functions have names that are informative. So make sure that they are kind of self-explanatory and it's easy to understand what they mean. If they are not, make sure that you have good documentation to explain what each object you created or each variable is. Other good practice, try to not leave clutter around. So if there are data or scripts you don't use anymore, if there's code that you don't use anymore, delete it and just make sure that you have only the essential things for your work. If you create new variables and try to have labels or attributes to explain what they mean. If you don't have that, try to create a dictionary for your data. Again, this will ensure that other people understand the data that you have and you can share it with others as well. Also, you need to be careful with the naming of your files. So this is a kind of classical example of naming files with final and then different later versions appearing and then things become very unclear which file came first and who modified it and so on. So try to have a convention on how you name your files and try to be consistent. And if you are part of a bigger group, try to discuss this with your colleagues and be consistent with your collaborators. And this is where version control comes in. So naming of files is a little bit like a version control. So you're saying, oh, this version of the file is different from the previous one. You might make clear who maybe modified it or the date when it was modified. And this is where version control comes in, because this is an automated way in which we can have a history of all the changes we have done. And probably the most popular platform for version control is Git. And then there's also a platform online for storing and sharing this information, which is called GitHub. So we'll discuss a little bit about that as well. So version control was initially developed by software programmers, and it's a way to kind of track the development of software. So it's a way to see who changed what and have an entire history of all the changes that were introduced to the code. And it's designed to maintain a very detailed record of all the changes that have been done, and it facilitates collaboration with other people when working with code. And Git in itself, it's quite complex. So in the background, Git can do lots of things, and it's a complex software. But for applied quantitative researchers, there are actually only a few essential things that you need to know. And for the most part, you can work just using those. If you are interested, there's more materials online, and you can spend a lot of time understanding, how this software works. A few basic concepts. Git is organized using repositories. So these are a little bit like the Rprojects, or a little bit like a working directory. So these are a space on your computer where you have everything that is related to your project. And when you do changes that you want to kind of keep with your files, what you do is you add the files to a staging area. So this is a place where an intermediary place where you put all the changes that were produced in your repository or your working directory. Once you're happy with those changes, you can commit them. So for each commit, you need to write some text to explain what is the change, and then submit them. And Git will remember that point in time. So it will know that a particular change has happened in the repository. It will record that change. It will have a timestamp. It will be clear what were the changes, who made them, and also there will be this comment that explains what is the change. So it's really important that you have these messages for each of the different commits that you have. Git also allows you to have branches. So normally you have a master branch, so a main, the main version of the code. But if you want to experiment, and let's say you want to try different things with your code or upgrade your code, you can create a branch. So this is a way to create a safe environment in which you can experiment without modifying or introducing errors to your main code. This is really important, especially for large projects. Imagine you have something like a website or an app that is live and is, people are working with it, and you want to upgrade it or improve it. So you want to keep the master branch safe and have only things that you are sure that are working there. But if you want to improve it, you can create a branch, work in this branch, create changes that you want. And once you are ready, you can actually merge it with the master branch and improve the code. So this is a way in which you can iteratively experiment without threatening the integrity of your master branch. Other things you can do with a Git, you can clone it. So let's imagine somebody created a Git repository online, and you think it's interesting and you want to maybe develop it further or just play around with that code. You can just clone it, and that means that you're making a local copy of that particular repository that you can work with. If you think that in the future you might want to propose changes to the original repository, you can actually fork that repository, and then you can create something called a pull request. And that would basically notify the owner of the repository that you have made some changes and you propose that they are considered for the master branch, and they can evaluate your proposal, and then it can be integrated with the original repository. So again, this is a way in which you can contribute to projects with other people. Each commit has something called a hash, and you can actually use that hash to go back in time. So this is again a way in which you can back up your code, because you can go to previous versions of your code, and even to particular versions of a particular file, in order to find the changes that you have made. You might want to keep some of those changes or modify them further. And if you want to get your files from a commit, this is called a checkout. So you can check out your files to use later or to share with other people. So Git is the system that works locally. So on your computer, you have this software, and you can have a history of all the work you have done. So you can make some changes to your code, you can commit them, and everything is stored locally. But if you want to collaborate with other people, you have to use some kind of server in which multiple people can see these changes that you're creating. Probably the most popular platform for this is called GitHub. So GitHub is just basically a repository of Git repositories, and here you have lots of different projects, and you have collaborators that can modify and contribute to code. So in addition to committing your code to the local Git, now you can do two other things. You can pull your code, in that way you're getting the latest version of the code from GitHub. So imagine one of your collaborators has added a new script to do some new analysis, for example. Then you can pull that code, and on your computer you get the latest version of the code with all the changes they have made. Then you can also do your own changes, so you can create new code or modify existing code, and then you can push it. And pushing it basically says, take the current version of Git, of the Git repository on your computer, and send it to GitHub. And that way it will be available for other people. So again, this is a way in which you can back up your work and in which you can collaborate with other people. And Git and GitHub also have different tools to deal with conflicts, to review code, and so on, to facilitate collaboration. When you use GitHub, it's recommended to create a README file. So this is an example of a README file. So this is just basically a text file where you give some information about your repository. So here, for example, we have a title, we have some information about the work that has been done, some information about the data that was used, some information about the files that are in the repository, and then the session info for the software that was used. So it's always a good idea to have a very clear README file that other people can just read and understand what's happening in the repository. And again, here we see why it's really important to have something like session info, because other people could try to reproduce your work, and they can see exactly what version of the software you have used. Other important concepts from Git are tags. So this refers to the version of the project you're working on. And then there's also this concept of diff. So these are the differences between commits. And basically it just shows what text is different from one version of your repository or file to another one. And this is how actually Git stores information in the background. It doesn't store all the files, but it stores differences between files. And this is kind of a very easy way to find how the code has changed in time. Another useful file and concept with Git and GitHub is gitignore. So gitignore is a text file that exists in your repository, and here you can mention all the files that you want to be ignored and you don't want to share. So imagine there are some byproducts that maybe you don't want to share, or maybe there's some data that you don't want to put on GitHub. You can just mention them in this file, and they will not be pushed to the GitHub repository. So here, for example, there's some types of files we don't want to include. So all the files that have .aux and .bbl, they will not be put on GitHub. And also all the files that are in the cache subfolder, they will not be shared. So this is a way to make sure that you don't share any sensitive data, and also make sure that you only share the essential things on GitHub. Okay, again, it's very important to keep in mind that the commits that you write are very, very important. So whenever you submit a commit, you need to have this comment associated with it, and it's very important that these are informative. And you need to find a good equilibrium between how often you commit, because every time you commit, you need to put the comments, and it is more work. So you need to find the equilibrium where you don't commit too often, but often enough that you kind of capture all the main changes in your code. As time passes, this can become more difficult and time consuming. So it's good to find this equilibrium early on. So why go through all this trouble? What are the big advantages of version control? So first of all, you can always jump back in time. So you can go to any file at any previous commit and see what you have there. So if you made an error or you want to find some old code you have, it's always possible to do that. You can also selectively undo earlier commits. So you can undo just for some files, for example, go back in time, and for the others, you can keep the current version. If you use code, anything that is text, GitHub can very easily highlight all of the differences that exist. So it's very easy to find, okay, what was deleted, what was added, and facilitate kind of your the tracking of changes. And also, Git and GitHub offer this this idea of a branch, a way in which you can safely test your code. If we use the GitHub, so the version with the server, this is also a very powerful tool for collaboration. So we saw that people can push and pull things from the server. You can also comment and give feedback to other people's code. You can have someone that could evaluate all the code that is submitted to make sure that there are no issues. And also, it's a very useful way to back up your code. In addition to this, GitHub also has a number of other services that are very useful. So one of them, for example, is Zenodo that you can use to get a DOI. So DOI is a way in which people can quote or cite your work. And as code becomes more and more important, you can actually get a DOI for the code you used to create, let's say, do some analysis or for a package. And people can cite your work. So it's a way in which you can actually make your work more visible and also get credit for what you have done. So let's discuss a little bit how to interact with Git. And there are a couple of different ways to do that. The original way, and one way to do it, is to use the Git command line. So this is kind of its own language. It has particular commands you can use to do the things that we discussed, from committing to pushing and pulling and so on. As you can imagine, it takes a long time to learn that, and there's specific commands that you need to learn. There are alternative ways to do that. One is to use something like GitHub Desktop, but there are also other alternatives out there. And these are basically interfaces that you can use to do the things that we have discussed. So GitHub Desktop is the version created by the people from GitHub. And like I said, there are multiple different software that were created to help you facilitate this process. If you work with something like Rstudio, also they have their own kind of interface with Git. So once you connect Rstudio with your account on GitHub, you can actually do the things we discussed directly from Rstudio. So this is an example of using command line with Git. So for example, if you want to define your user and your email address, and then see what other options and settings you have, you can use this kind of commands. And it's very easy to look up different commands depending on what you want to do. Alternatively, you can use these interfaces. So what you have here is an example of the GitHub Desktop. And here on the left side, we have the new files that were changed. So files that are with orange, they were changed. Files that, for example, are with red, they were deleted. Files that would be with green, they're new files. And then if you click on a particular file, you can see what's new, what has changed. So for example, here for the git ignore file, we see that we added 2 lines, lines 10 and 11, where we ask for any CSV file not to be included in the sharing on GitHub. And then if you want to commit this, where it says summary and required, you need to put your commit comment, and then you press the commit button. And once you do that, a button will appear. So if you want, you can also push it to the server. So it's also available on GitHub. So using something like GitHub Desktop is kind of a way to streamline your work and just makes things much easier. Alternatively, this is how the Git interface from Rstudio looks like. Again, there's an initial step where you need to set up this on Rstudio. Once you do that, you have this interface where you can choose the files that you want to commit. Again, you see all of the changes, what was deleted, what was added. You need to add your commit message and then press the commit button. And once you're ready, you can press the push button. So just kind of to give you an overall workflow with Git, especially if you have a larger project. Normally, like I said, you have a main branch, and imagine this is the main code. If, like I mentioned before, you are in a big team and you have, let's say, a website or an app or, let's say, some kind of workflow that cleans your data. Let's say you don't want to mess with that if it's actively used by other people. So you can create first a branch, and this, like I mentioned before, is a place where you can safely make changes before modifying the original branch. You can add commits, so you can change code, experiment, and once you are ready, you can open a pull request. So this will inform whoever is the owner of the repository and who owns the master branch that you are proposing some changes. They can next evaluate what you submitted, so you can discuss and review and make final decisions. And once they agree with what you have done, they can be deployed, and finally it could be merged with the main master branch. So this is a way in which you go from experimentation to review to deployment, and then can be used in production. You can learn more, so if you want to learn generally about reproducible research, and version control and workflows are just a small part of what you can do to have kind of more transparent and reproducible research workflows. You can have a look at the first book here, and the second one is more focused on how to use R and Rstudio to have more reproducible research. And if you want to look at other examples, how to organize Git, you can have a look at these links here. Again, people organize work differently depending on what are their aims and their background. And it's good to see a few different ways to do this and then decide whichever works best for you.
Thank you for watching. For more information, visit our website www.radiance.org.uk.